Right, so 4.10 deals with properties of matrix transformations. So if T is a matrix transformation for R from Rn to Rm, then the set of vectors in Rn that maps under T to the zero vector in Rm, that's called the kernel of the linear transformation, and it's denoted by that quantity there. Right, so the set of all vectors in Rm that are images under T of at least one vector in V is called the range of T. Right. Okay, so the range should already be a familiar concept. And it is denoted by R of T. So it's just the range is pretty much the images that you get if you let T act on the whole of the domain. That will be the range. Right, so just as an example, here they give us a linear operator, and they give it with that formula there, and they just ask us, find the kernel and the range of T. Alright, so there's T in the point x, y. So what is the kernel? It's just all points x, y that map to the zero vector. So it's all x's and y's such that, so it's all points in the in R2 in this case, such that the image of those points have to be the zero vector. Right, and that's the same as saying that it's all points in R2 such that the image of that x and y under T has to be the zero vector. And that's just all points that lie on the straight line x minus 3y equals 0. So just rewriting that, we get... Right, so we can just write that as all points with x component x and y component a third x, and x is just a real number. Right, so that's a different way of writing it. So that's the kernel of T. Okay, so let's look at the range, which is the images of all the points x comma y. So just observe the following, that you can write that vector as a sum between these two vectors here. So let's just go and represent these points on a two-dimensional surface. Right. So let's look at the BA plane, and if we look at this point here. It's a point where all the it's a point where the first component is a value x and the second component is minus 2 times that value x, and the other point is if we take the first component being minus 3 times a value y, then the second component is minus 2 times that first component. Right, so those are all points that lie on the straight line b equals minus 2a, right? Now if you take the sum between any 2 points on that straight line, say b1a1 and b2a2, if you take the sum between those points there, right? Right, so you take the sum between those two functions, you can see again it is just going to be on it's just going to be on the straight line again. So if you sum these 2 points together, it is just going to be again somewhere a point on that straight line. So what is the range? The range is composed of all points. The range is going to be it's going to be the set of all points, with the first component being a real number and the second component being minus 2, that real number. Okay, and again a is just it's a real number. Okay, so that's the range. It's pretty much it's all points that lie on this straight line. It's all points that lie on that straight line. Okay, so this is just a formal way of finding the kernel and the range of a matrix transformation. So to find the null space, we find the null space and the column space of a standard matrix A of the transformation T subscript A, and then all you do is the null space of that matrix A will be the kernel of the function T subscript A, and the column space of A is pretty much going to be the range of of T subscript A. So just quickly again, so there you've got the representation of T subscript A in the vector X, and the vector X in this case is this vector here. So so again, looking at the kernel of this function, it's pretty much looking at all the x's that map to the 0 vector, and that is just equivalent to pretty much equating that to the 0 vector, and then solving solving for your x values that give me that, and that is just the null space. That's the null space of the function T subscript A. Now if we look at the range, recall that we can write this matrix product, we can write it as a linear combination of the column vectors of this particular matrix, right? So there we've got the second column, right? We have up until the last column. All right, so again, right, so we've got equality between these two things. Now again, these vectors come from the column vectors, and so that it forms part of the column space of the matrix A, where A is this matrix here, right? A is that matrix there. So basically, for a point to be in the range of that function, it needs to be a linear combination of the column vectors of the matrix A. Okay, so in the case of the function T subscript A, it's easy to find the kernel and the range. The range is determined by the column space, and the kernel is determined by the null space. Right, so now we look at just compositions of matrix transformations. If you have one matrix transformation from Rn to Rk, you've got another transformation from Rk to Rm, then then if we look at the composition between the two functions, right, that is going to be a new transformation that's going to take Rn to Rm. Okay, and the composition is just pretty much denoted by whatever you write closest to the point X, you're going to apply that first to the point X, right? And then that whatever result you get at the end you're going to apply that, then you're going to apply TB to whatever you get after you've applied TA. So you're pretty much working from your innermost right to your outermost left. Right, so you're pretty much going that direction there. Okay, so basically it involves multiplying first with A and then multiplying with the matrix B. So in particular, we observe that TB, composition TA, is just T, the function TBA. Right. Now note that the codomain, or the range of TA, is pretty much contained in the domain of TB, and that is necessary if you do a composition. Right, so you need the codomain there is contained in the domain of TB. Okay, so just a quick note on notation. Since any linear transformation from Rn to Rm is in fact a matrix transformation, we shall adopt the convention to denote its standard matrix simply by T, and using this notation, given two linear transformation T1 and T2, we have then that the composition can be given by the product between those two standard matrices. Okay, so let's look at a diagram in terms of the composition between TA and TB. So again, for illustration purposes, TA takes a vector in Rn to a vector in Rk, and TB takes a vector in Rk to a vector in Rm. So, alright, so how this works is, right, so T takes U or T subscript A takes U to T subscript A U, and then TB, right, takes that point there to a point there. And that point is this point here. Okay, so it's pretty straightforward. Okay, so next we have the example. Suppose the linear transformations T1 and T2 are given by this transformation and that transformation respectively. Then they ask us to determine if the compositions T2 with T1 and T1 with T2 are defined. And if they are defined, we need to find the domain and codomain, the standard matrix, and a formula for the composition. So observe that T1 maps points in R2 to points in R2, and T2 maps points in R2 to points in R3. Right, so again, you can just look at the diagram there. You can clearly see that T1 maps a point in R2 to R2, and then T2 goes. If we now look at the composition T2 with T1, that is going to clearly take a point there and map it to a point there. So it is clear that this T2 composition with T1 is definitely defined. But if you look at T1 composition T2, so T2 takes a point in R2 and it maps it to a point in R3. Now the question is, can T1 map a point in R3 anywhere? No, because T1, the domain of T1 is R2. The codomain of T2 is R3, and T1 doesn't act on any points in R3. So T1 can definitely not map a point in R3 there, so that is not going to happen. So therefore, Right, so therefore T2 composition T1 is defined. Right, and T1 composition T2 is undefined. And it is undefined as the domain of T1 is R2, but the range of T2 Okay, so we established that T2 composition T1 is the only one that exists between the two compositions. It is clear that the domain of T2 T1 is R2 because we first let T1 act on the point xy, and the point xy is in R2. Right, so now we need to determine the range. So it would be helpful if we can just determine a formula for the composition between T2 and T1. All right, so first, T1 sends the point x comma y to 4x minus y, and then letting T2 act on that point, we get a point in R3. Right, so we get that point there, so that gives us a clue as to what exactly the range of this function is going to look like. Okay, so if we look at this point here, we see that it's a point in R3 where the first two components I add them together, and I multiply with minus 1 to get the third component. So essentially that you can view that in fact as points that lie on a plane. So if we go to 3 space, you're looking at all points P where you construct the third component by adding the first two and multiplying with minus 1. So that's essentially the plane that I take if we look at a CAB axis, we're looking at the plane C equals negative A plus B, right? So it's all points that lie on that plane. Right, so the range of T2 composition with T1 is simply all points in R3 such that those points are points that on the plane determined by the third component, which is this component there. All right. So let's look at finding the standard matrix. We've found the formula for T2 composition T1. What is the standard matrix? Right, so there's the standard matrix for T1. Okay, and for T2, so there we've got T2, which is that standard matrix there, and getting the standard matrix for the composition to take the product between the two. Right, so there we go. And we take the product between those two matrices to get. Alright, so there's my standard matrix for the composition. Alright, so we have the two concepts of one-to-one and onto. So when is a linear transformation 1-to-1? We say it's 1-to-1 if T maps distinct vectors in the domain into distinct vectors in the codomain. Alright, let's look at the diagram. So what does it mean for a function to be 1-to-1? It maps distinct vectors in the domain to distinct vectors in the range. Right, so that's how it works. So if we are to ask to show that a linear transformation is 1-to-1, we need to do the following. Right, so we take 2 points in the domain and we look at their images. We equate their images there. So equate those 2 points there. And we know that T maps U to that point and T maps V to that point there. And then, having done that, we need to then show that U is equal to V. Right, so we need to show that, in fact, we need to show that that happens. We need to show that U is actually equal to V. Right. Alright, so the second onto concept, we say that a linear transformation is onto if every vector in the codomain, for every vector in the codomain, there is a vector in the domain that maps to it. Right, that's the same as saying that for every vector in the codomain, it is the image of at least one vector in the domain. I pick a vector in the codomain, pick an arbitrary vector. So now I need to go and show that somewhere in the domain there is a vector U, right? Such that if I look at the image of U, we have the following. We have in fact that that the image of U is in fact this point V. Right, so T of U is basically equal. And that's for every vector. For any arbitrary vector that you choose, you need to be able to do this for it to be onto. Okay, so theorem 1 speaks a little bit about linear operators. Now, if T is a linear operator from Rn to Rn, and A is the standard matrix of T, then the following statements are mathematically equivalent. That is that A is invertible if and only if T is onto, if and only if T is 1-to-1. So why is this the case? Why are those three statements mathematically equivalent? Right, so we claim first that A being invertible is equivalent to saying that T is onto, right? So let's assume first that A is invertible. Right, so we assume first that A is invertible, and now we're going to show that T is onto. So how do we show T is onto? You take a point in the codomain, and then you show there's a point in the domain that maps to it. Right, so let's let's take a point in Rn. Okay, that's the codomain. Right, and we need to find a point in the domain that maps to it. Right, so what we're going to do is we're going to consider the point U, and we're going to multiply it with the inverse of A. Right, now that point is definitely an Rn. If you take an n by n matrix and you multiply it with a a column vector with n rows, you're going to get a vector in Rn. Okay, and that is the domain. That point is clearly in the domain. Then if you look at this, because A is a standard matrix, if you look at T, if you look at T in that point, okay, what it does is it maps it to that point, and that is U bar. So we have shown that there's a point in the domain, which is that one there, that in fact maps to the point in the codomain. So that is clearly it's clearly onto. All right, so hence T is onto. Now, now we need to prove that if T is onto, then A is invertible. Right, so assume T is onto, and we show that A is invertible. So what I'm going to do is I'm going to show that A is invertible, we're going to use the equivalence theorem. So I'm going to take a vector B in Rn, which is the codomain. Right, so since T is onto, there exists a vector X in Rn, which is the domain, such that T maps X to this vector B. Okay, so what's the implication of that? We know what T does, which will imply that A X bar is equal to B bar. Right, so the system, AX bar equals B bar has a solution, or is consistent. It's consistent in by one vector. Okay, so by the equivalence theorem, A is invertible. Okay, so that takes... Alright, so next we prove that if T is onto, then T is 1 to 1. Alright, so we're going to assume T is onto. Okay, so by the previous claim, A is invertible. Right, so how do we show T is 1 to 1? Is we take U and V both to be vectors in Rn, such that so t in the point u, set that equals to t in the point v. So that is going to imply that AU is equal to AV, which is going to imply that U is equal to V. And that is true because A's inverse exists. Because remember we said if T is onto, then A is certainly invertible. Right, so our last claim is that T is 1 to 1. If it's 1 to 1, then A is invertible. Right, we're going to use the equivalence theorem again. So what we're going to do is assume T is 1 to 1. Right, now what we're going to do is to consider the linear homogeneous system. Consider the homogeneous linear system AX equals 0, right? To show that A is invertible, we need to show that this system only has the trivial solution, okay? So we want to show that x bar can only be the 0 vector. Now we know that T in the point x bar, we know is definitely a x bar, and that we set as the 0 vector, but we know the 0 vector is also T in the point 0, okay? Because remember we say T in the point 0 is just pretty much the matrix A that you multiply with 0, which is the 0 vector, okay? Right, so from there it follows that T x bar is equal to T in the point 0. So that should be a 0 bar, okay? And because T is 1 to 1, it means that x bar is equal to 0 bar, okay? T is 1 to 1. All right, so by the equivalence theorem, A is invertible as AX bar equals 0 bar has only the trivial solution. Right, so we've proved our claim. Right, so going back, we have shown that A is invertible. It implies that A is onto, and A is onto implies that A is invertible. We showed that if T is onto, then we've showed that T is 1 to 1. And we've also shown that if T is 1 to 1, then A is invertible. Okay, so T is 1 to 1, implies A is invertible, which implies T is onto. So you could also have that if T is 1 to 1, it implies that T is onto. Right. So therefore those three statements are mathematically exactly the same. They're equivalent. Okay, so in this example here, they let T be a linear operator from R2 to R2, and it is given by this formula here. T takes the point xy and it maps it to that point. So now they ask us, is T 1 to 1? Is T onto? Okay, so let's first investigate whether T is onto. So just to recap, what exactly do I need to do to show that, that the onto property holds? Alright, so let's look at a diagram again. So T goes from R2 to R2. So what does it mean for me to show, to try and show that it's onto? Right, so to show that it's onto, I need to select a point in the codomain. Right, let's call that point x prime, y prime. And I basically want to find a point in the domain such that T maps the point xy to the point that I chose. Right, so what does T need to do? T needs to map that point to that point there. That is what it means to show a operator T is, well, this function T is onto. So again, I need to select, be able to select an arbitrary point in the codomain, and I need to show that there's a point in the domain that maps under T to that chosen point. I need to be able to do that for any arbitrary point x prime, y prime. So let's select an arbitrary point in the codomain, call it x prime, y prime. Right, now to establish whether in fact T is onto or not, I just want to see what needs to happen for a point in the domain to map to this particular point x prime, y prime under T. So what does my point x, y, what does that need to look like for it to map to x prime, y prime? Right, so if T in the point x, y is equal to x prime, y prime, for some point x, y in the codomain, in the domain, what do we need to happen? We need pretty much, we need x prime to be equal to x minus 3y, and we need y prime to be equal to minus 2x plus 6y. Right, now the question is, does this always happen? Right, so there we've got the two expressions. Okay, so therefore we need, for this to happen, we need x prime to be x minus 3y, and we need y prime to be minus 2x plus 6y. And basically, if you take twice 1 and you add that to 2, you pretty much get that y prime plus 2x prime needs to be equal to 0. Okay, so that gives me sort of a clue as to whether this thing is onto or not, because now I can choose y prime and x prime in such a way that this equality is not satisfied, and that is going to give me a problem with it being onto. So let's just see. Let's pick an x prime and a y prime. Okay, so our proof can basically now proceed. So let's pick an x prime equals 1 and a y prime equals 1. Right, so I'm going to claim that T is not onto. Let's assume to the contrary that it is. Okay, so assume to the contrary that T is onto. Well, then there exists a point xy such that t in the point xy is equal to the point that we chose, which is 1, 1. And that happens if and only if, what does t do to xy? It sends it to the point x minus 3y minus 2x plus 6y. Okay, that's what it does. And we need that to be 1, 1. And that happens if and only if x minus 3y is equal to 1 and minus 2x plus 6y is also equal to 1. Okay, so what can we say from there? Right, so take that expression there, and we're going to add that to twice to that expression there. Right, and we know that that is equal to 1 plus 2, which is equal to 3. Okay, and what is... Okay, and so from there, that implies that that 0 is equal to 3, contradiction. Okay, so this function is clearly not onto. Okay, so illustrating that again with a sketch here. So if you look at this point in the codomain, and you look at any point in the domain, if you let t act on that point, it's going to map somewhere there, but it's never going to map to that point there. Okay, so it doesn't matter what you make x or y, it can never map to that point there. So therefore, this function